On the screen, we show the rate experiment setup with the conical flask fitted with a tight bung and delivery tube leading either to a gas syringe or to an inverted measuring cylinder in a water trough. And the aim is to see how concentration changes the rate of the reaction between hydrochloric acid and magnesium while we measure hydrogen gas. The apparatus panel lists a stopwatch, a thermometer, a ruler and scissors for cutting equal strips of magnesium, a balance for checking mass, a clamp stand to hold the syringe or cylinder, and safety goggles because accurate measuring and safe working make the test reliable. A particle animation now explains the idea that a higher concentration means more reactant particles in the same volume, so collisions happen more often, and a greater fraction per second are successful, which increases the rate. We begin by preparing equal magnesium pieces by cleaning any oxide with emery paper, cutting to the same length, noting the mass, and keeping the surface area constant so that concentration is the only major difference. Next, we measure a fixed volume of hydrochloric acid into the flask, record the starting temperature, and prepare several concentrations from a stock solution by mixing measured volumes with distilled water so the concentration is known. We then add the magnesium quickly to the acid, seal the flask immediately, start the stopwatch, and record the volume of hydrogen at regular times because the gas volume shows how fast the reaction proceeds. To make a fair test, we repeat the runs for several acid concentrations while keeping temperature, total volume, magnesium mass, and surface area constant, and we take at least 2 repeats at each level to allow a mean. During each run, we plot the gas volume against time graph and read the initial slope as the initial rate, while the final flat part shows the total volume when the reaction has finished and the limiting reagent is used. We then draw a graph of initial rate against concentration, and we see that the rate increases as concentration increases. And in this school system, the points pass close to the origin, which suggests a directly proportional relationship. As a quick alternative, we can time how long each run takes to reach a fixed gas volume and compare these times, because a smaller time means a faster rate, and this method is easy for classroom data capture. Safety and quality reminders appear, including wearing goggles, handling the acid carefully, sealing fast to avoid gas loss, checking the syringe zero and seal to prevent leaks, keeping the temperature steady, and disposing of solutions safely. Finally, we interpret the pattern by linking the steeper starting slopes at higher concentration to more frequent effective collisions. And we finish by tidying the bench, drying the equipment, and writing conclusions, uncertainties, and possible improvements for a future run.